Yeah, that's right. So yesterday when we did our chapter 14 notes, we didn't get to this page right here, page 5. So I do want to start by doing some of these problems, and then we'll go through some of the homework together, okay? And see if by the end you've really got a handle. On the lesson plans for the day, there wasn't any new learning. It's really just making sure that you're comfortable with the material so that we can do the warm-up, page 11 for homework, and the quiz for chapter 14 tomorrow. So here we go. So on page 5, the first problem is number 5. It says there are 5 multiple choice questions and there are 4 possible answers. So I want you to think about it. If there are 4 possible answer choices, if you randomly guess, what's the probability that you will get a correct answer?
25%.
Okay, good. 25%. So 1/4, or you can write it as a decimal, or you can write it as a percent. One other thing that I noticed is that you really should be able to go seamlessly from decimal to fraction to percent, because you may have it in a different format than me, and all of them are equally fine. So I really don't want you to say, well, I read it as a decimal and blah, blah, blah. Any of them are fine as long as they're equal. You need to be able to flawlessly go between. All right. So the probability correct is 25% or 0.25. What's the probability if you just guess that you get none of the questions? Keep in mind there are 5 questions. None of the 5 questions are correct, so the first one is not correct. And the second one is not correct. And the third one is not correct. And the fourth one is not correct. And the 5th one is not correct. They're all wrong. So because I need all of that to happen at the same time, that's an intersection. So we're going to be multiplying those numbers together, because I need all those to happen at the same time. So what is that probability of getting it wrong if getting it correct is 25%?
0.75.
Good. So this one's 0.75. Okay, so they're all your 0.75s. Okay, and so then if you write the problem like that, that's fine. You should start to bridge to writing it this way, 0.75 to the 5th power, and not freak out about that and go, where'd you get that? It's because there's 5 0.75s there. All right, so you can do the decimal. If you do the decimal, it's 0.2373. If you do the fraction, I think it's 243 out of 1,024. So either of those answers are good. And if you did the decimal and maybe you want to then turn it into a fraction or whatever, you know how to math fraction in your calculator? Okay? Yes.
Amount of decimals or sig matter?
So significant figures needs to be at least 2. Okay? So I would leaving this as 0.24 is perfectly fine. Okay? But a minimum of 2 significant figures. All right. How about getting all 5 of the questions correct?
0.25.
Good. So that looks like the first one is correct, and the second one is correct, and the third one is correct, and the 4th and the 5th are all correct. And correct being 0.25. And you're going to be multiplying all those together. So essentially, it's 0.25 to the 5th power. But I wanted to just show you where that's coming from. Again, in these baby steps, I wanted to show you where we're getting all of these things. Is it very likely that you are going to randomly guess and get all 5 of them correct? No.
0.98.
Yeah. It's 0.00098. That is your 2 significant figures, which I think is 1 out of 1,024. If you wrote it as a fraction, not very likely. I mean, that's 0.098% chance. I mean, that's so small. Ooh, here is our get at least 1. So remember yesterday that we had kind of a little special, that was a special situation when we have at least 1. What was the little deal?
1 minus p.
Probability of none. Okay, so my little song went probability of at least 1. Listing all the combinations is not fun. Probability of at least one. It's easier with 1 minus the probability of none. Okay, that's the key. 1 minus the probability, but I want to teach you how to write out the none part. So I always start off, I make it a little 2-lined thing. 1 minus the probability of none. None what? None of the, how many things are we talking about here?
5.
None of the 5. And then it's what it says up here. None of the 5 are wrong. So that's how you know what goes in that little section there. The probability that none of the 5 are wrong. Okay, what does it mean if none of them are wrong?
It's all right.
They are all right. So none of them being wrong is the same as this part B. Okay, see, none of them being wrong is that right there. So we're essentially going 1 minus the 0.00098, which is 0.99902. You could write it as 99.9% chance. So that's a really high chance that you're going to be getting at least one of them wrong. 99.9% chance you will get at least one of them wrong. And of course, if you had that as a fraction, it's 1023 out of 1024. See, because it's the other ones besides that one right there. Okay. And then the last kind of problem, the first incorrect answer is on the 4th question. So that's defining the order. So let's imagine our first question, second question, third question, 4th question, and 5th question, okay? So the first time I get an incorrect is where? In that 4th spot. So I know that 4th one is wrong. What does that mean is in front of it? They're right. So that one's right, and that one's right, and that one's right. Now, does it define what has to happen after that?
No.
Okay, so this one does not matter. And when I say it does not matter, that doesn't mean you get to pick. That means it can be right or it can be wrong, and we'll look at that in just a minute, okay? So we'll look at the math that goes with that in just a minute. So what's our number that goes in the first problem? Our percent chance. Okay, our probability is 0.25, 0.25, 0.25. I need the first one correct, and the second one correct, and the third one correct, and I need the 4th one wrong. And look here. This last one can be right, or is addition wrong? So the probability in the last box is 100%. So essentially, I have a 1 right there. Does a 1 right there change anything's value? No. So technically, you don't even have to include that last one because it's not specified at all because it's just 1. Okay? It didn't specify what happens at the 5th question, so it didn't have to be included. Okay, but technically, if you included it, it doesn't change the value. Okay, and then you've done the math. I don't know what that is. Oh, I think it's 3 over 256, and then 0.1 or 0.012, because it's 1/7.
2%. Yeah.
Oh, okay, then you did percent. Okay, 1.2%. Got it? All those are correct. See, all these different formats, and then the full decimal was 0.01171. So, I mean, there's all these different kind of answers, and one of the things you are learning is how to compare those. Okay, so how does that look? Did you follow all of that? Did that feel better than, okay. So then tomorrow we're going to end up doing this law of large numbers lab. We don't have time today. So let's go on to the homework. So the homework you had last night, we skipped problems 7 and 8, and let's look at 9. So a lot of people were very unsure about what the heck is 9 even asking. Okay, but I think whenever I start talking to you about what it is asking, you're going to be like, oh, well, that makes sense now. Okay, so it wants to know, this is a spinner. And I want to know, are these probabilities on the spinner a possibility? Okay, so for example, if the first spinner had 25% red, 25% yellow, 25% green, and 25% blue. Is that a possibility? Could you have a spinner like that?
Yes.
Yes.
Because it adds to
Because they add up to 100% and all the colors are just a fourth. Okay? So then they did another spinner. So envision this spinner. This is a separate spinner. Could you have 10% red, 20% yellow, 30% green, and 40% blue?
Yes.
That totals up to 100%. So yes, you can have that one. Okay, let's do this next one. 20% red plus 30% yellow is 50% already. And if you add 40% green, you're at 90%. And then you add in that blue, what does that give you?
Over 100.
140%. Can you represent 140%? No. Because you cannot have over 100%. Can't have 140% represented on a spinner. Okay. All right, this is an interesting one. How about this one? 0, 0, 0, 1, 0. Is that a possibility? What does that spinner look like?
Just one green thing.
It is solid green spinner. Doesn't give you much. It's not very interesting. Are you going to get green? Yes. Are you going to get green? I'm going to bet green. How about that? Let's bet green. Okay, but that is possible. It's not very interesting, but it is possible. Now, this is an interesting one. 0.1 plus 0.2 plus, what does this mean? How much of this spinner is green? 120% of that spinner is green. How much of the spinner is blue?
Negative.
What? How can you have a negative percent? So is this a possibility? No, because you can't have, of course, over 100%, and you can't have negative percents. Okay. All right, so then I'm going to continue kind of going through these with you. By the time I do I'm going to do one more page and a half. And after that, I think, as per my other classes, then they were really starting to get the hang of it, and then they were feeling very confident. So let's continue with this problem number 11. Is that okay with you guys?
Yeah.
All right.
Perfect.
Here we go. Number 11. A consumer organization estimates that over a 1-year period, 17% of the cars will need to be repaired one time. So the probability of one repair is 0.17. See, and sometimes I write these as decimals, sometimes percent, sometimes fractions. I'm doing that one that way. The probability it needs 2 repairs is 7%. Okay? And the probability that needs 3 or more repairs is 4%. So that's what the problem says. So these are all of the repairs. So the probability that it needs any repair, what does this total up to be? 28%. How did you get that?
You added them.
You added 17% plus 7% plus 4%. So 28% of vehicles need a repair of any kind, of any amount, okay? If that's the case, what's left over? No repairs. And how many need no repairs? 72%. You got that from doing what?
Subtract.
1 minus the 0.28. Okay, so here we go. Now's our questions. You are going to choose just one car. So we're just picking one car. What proportion of them need no repairs? What's the probability? 0.72. Very good. Okay. What proportion of them need more than, no more than one. Oh, okay, no more than one. Okay, I got to think about that. Yes? Uh-huh.
So it says the probability of 2 is 0.7, but like if you're going to add them together, if the car has already taken 2 repairs, that means that it's already had 1 repair. So
Okay. I understand. And so that's not what this means. That's why I wrote the little word exactly one. So exactly one repair. Exactly 2 repairs. Not meaning 2 or less. Yeah. So we're not double counting. Correct. You are absolutely right. At one point it was confusing, and you could interpret it different ways. That's why I hand wrote in those words exactly, so that it was clear that we're not double counting. Okay? All right, good thought. So on this one, no more than one. Man, these always mess up my brain. I don't want more than 1. So I don't want 2, and I don't want the 3 plus. I want...
No repairs and 1 repair.
Okay, good. I want the no repairs and 1 repair. Those are good. So that means I need to add together the 0.72 plus the 0.17, and that equals 0.89. Now at this point, I'm going to tell you about what work you need to show. At this point, I'm going to tell you if all you wrote down was 0.89 on the AP test, you would have gotten it wrong. On the AP test, they want to know where this comes from. So you would need to show that you're adding together the 0.72 and the 0.17, or you could show this. So you could show either one of these things right here, but you have to show your work. You can't just put a number down. And that's for me too, since it's on AP as well. All right, some repairs. What does that mean? You need any amount of repairs. We kind of already figured that out. Our work is up at the top.
28.
Yep, this section, so see our work is up there. So the AP would be okay with that, 0.28, because I already showed my work up there. Okay, now look at number 13. Let's examine how it's different. It says, consider again the auto repair rates in number 11. If you own 2 cars, what's the probability that neither will need a repair? So what's different about these ones than the one before? 2 cars instead of just 1. That means I have to address this car and the second car. The first car and the second car will be multiplying those probabilities together. That's the difference. Okay, so neither need a repair. So no repair times no repair. So I think that's this and this, which is 0.5184. So if you rounded it to 2 significant figures, so anything along those lines is good. Okay, how we doing? Okay? All right. Yes. Go ahead.
I'm still confused how you know whenever it's just a multiple.
Okay, so here's why I'm multiplying. Because I need my first car to need no repairs, and that's the key. And at the same time, the second car has no repairs. So that's multiplication, because I need that. And is multiplication, yep, because I need the first one and the second one to not have repairs.
What's or?
Plus, or is adding them. Okay, both of them need repairs. That means the first one needs a repair and, so that's multiplication. The second one needs a repair. They both need a repair. So what's this probability of a repair?
0.28.
Yeah, didn't we show that up above? Getting any kind of repair is 0.28, so it's 0.28 times my 0.28, and that's how you get that is, I think, 0.0784. And then, of course, you can do it to 2 significant figures if you want. 2 significant figures is not 0.08. Okay? This first 0 is not a significant figure, 0.078. That's 2 significant figures. Okay? Ooh, my favorite, at least 1. Because then I get to sing. The probability of at least 1 is 1 minus the probability that none of the what? How many? None of the how many. Okay, right. Always put the how many right there. None of the how many.
2 cars.
And then what is it talking about? Need a repair. So now I analyze that little piece. What does it look like if none of the two cars need a repair?
The 0.72.
Yeah. Oh, look at there. We did that right there. Ta-da! So that's going to be 1 minus my 0.52. And there it is.
Wait, 0.7. Wait, why is it not 0.7?
Both of them. It was the 0.72 times 0.72. See, neither of the two, right, need a repair.
Okay, that makes sense.
Okay. How you doing? Okay. Now, this one is not very intuitive, so let me kind of walk you through this. Plus, I want to kind of mention that if it was a multiple choice question, they might throw you some different language into it, and so I want to show you that. So look at this one here. Now, we were able to multiply like 0.72 times 0.72 and 0.28 times 0.28. What happened? Why were we able to keep the number the same from the first car to the second car? What did we assume?
That they're the same car.
Okay, so we assumed that the probability of a repair stayed the same. Do you agree with that? The probability of repair stayed the same from car to car. Okay, to me, that is a common sense statement. I like that statement. Educationally, they might try to throw in some statistics vocabulary. So let me tell you another way that this could be told to you that means the same thing. What do we know? What word did we learn yesterday? That means the fact that one thing had a repair doesn't change the probability that the other one needs a repair. Independent. So if this were, say, a multiple choice question, your brain may be thinking the first statement. However, an answer choice may say instead the probability rates are independent of the car. So the fact that one car had a repair didn't change the probability of the other one needing a repair. Now they're just asking for your opinion. Do you think that assumption is reasonable? If you have two vehicles in your family, do you think that one car's probability or repair rate is the same as the other?
No.
So I agree. I say no. Let's give a couple reasons. Why? Type of car, okay.
Different wear.
Type of wear, wear and tear, driver,
minor.
all those things. Okay, and so on. So I'm going to give a few specific examples to support my statement. Okay. All right. I'm going to do one more problem. I'm going to do the half of number 23, and then I'm going to set you free to do some on your own, and we'll then check as we go along. So look at this number 23. So the Master Foods Company says that before introduction of purple, yellow candies made, which is weird. Okay, so there's not really purple M&Ms, generally speaking. We were talking about this in an earlier class, except for, like at Easter, isn't there purple M&Ms at Easter? Don't they do the pastels? Yeah, they do the pastels. Okay, but anyway.
Wait, so it's not saying the purple and yellows make up 20%? It's saying,
no.
Oh, well, there's the
Before
problem.
purple, so the probability of yellow
That's a confusing question.
is 0.2. It says the probability of red is 0.2. Now, let's carefully read this language here. Look, orange, blue, and green each make up 10%. Does that mean they total to be 10%? No. Orange is 10%. Blue is 10%. And green is 10%. Okay, So then it says the remainder are brown. So we need to figure out how much is accounted for so far. Yes, if we totaled up 0.2 plus 0.2 plus 0.1 plus 0.1 plus 0.1, that's 0.7. So that remainder is that. No, these are not true amounts, and I'll tell you why. Because we will next semester, since we have to do chapter 16 right when we get back, it kind of messes it up. It used to be the first day back from Christmas we do an M&M's lab, and we get to actually eat them. But it's really interesting. Let me kind of give you a quick information about it because I love it. So the M&M's company, actually, I had to call them up. So I looked at the back of a package. It's the Mars Candy Company, not the Master Foods Company. It's a Mars. And I called them. It's a 1-800 number, and I asked them what their percentages for their colors are. And they told me. And so then we all got our own little package of candy, and we counted the proportion. We did just one color. We counted the proportion of blue M&Ms. And so we determined, how do our numbers compare to what they claim? Do our numbers support? There's going to be some sampling variability, but are our numbers around close enough to what they claim? Well, this is the cool part. One year, this was about 3 years ago, it was really far off, and I was freaking out. I was like, what the heck? Why are our numbers so different from what they have been in the past? So I called them back. Literally, I called them back and I said, hey, what's going on here? What are the proportions? And they said, where are your M&Ms from? They opened up a new factory that wasn't in Hackettstown, New Jersey anymore, but it was then in Tennessee. And so they had different percentages. And that ours came from that second factory that opened up. And so ours did support those numbers. So it was so cool that we discovered, oh my gosh, they're not supporting it. And I called them up, and sure enough, ours did come from a different place. So that was really cool. So we'll get to experience that. We'll see what's going on whenever we do ours when we get back in January. But let's go on. Here we go. So these percentages are not true because I know the other ones are something different. Okay, so look here. What's the probability that it is yellow or orange? What's the or? Add. So that means I want to know the yellow plus the probability of the orange. So somehow you need to show that work. And you could write that. Or you could just write 0.2 plus 0.1 equals your 0.3. But somehow show that work. Ooh, how about not green? Do you know that would mean the complement? Do you remember that from yesterday? Complement is all the other parts other than green. So how much is green?
10%.
Okay, so we got to do everything else except for the green.
So it's 90.
So that's 1 minus 0.1, so that is 0.9. Very good.
Can't you just...
You can just shortcut it, yes.
Okay.
But I'm kind of trying to guide you and refresh your memory on what complement means, okay? So educationally, I try to kind of pull those things together. How about the probability it's striped? 0. Okay, so now we're going to take a few minutes. I'm going to give you about 3 minutes to do this, and let's look at how are these different. If you pick, what? 3 M&Ms, not just one. So you need the first one to be brown, and the second one to be brown, and the third one, and so on, okay? So I'm going to pause for a minute here and let you do those, and then we'll check them. All right, let's go ahead and check these. There were your little hints. And so they're all brown, so 0.3 times 0.3 times 0.3, and I don't know the number value of this, so you can do it. Oh, yeah, that's right, 0.027. Not red is 0.8, not red, 0.8, red, and so I don't know what that is. Okay, so, okay, and then not yellow. So how much were not yellow?
0.8.
also 0.8. So these were all not yellow. So that was that, which is 0.512. Okay, and then look at our last one.
Wait, I don't really understand.
The last one.
Why would you do
So it's 1 minus the probability that none of the 3 are green. So that means not green, and the second one is not green, and the third one is not green. So this is 1 minus all 3 of them are not green. Okay, and so that's how you got.
Why would you do none of them are green?
Okay, so remember, 1 minus the probability that none of the how many, which is 3, and then you put down what this says. None of the 3 are green. Green is 0.10. So not green is 0.9, not green 0.9, not green 0.9. None of the 3 are green. Okay, so I don't, whatever that is, 0.729? Oh. Oh, okay, gotcha. Okay, so now you should be totally to your own on this one. Let me give you this whole page to do right now on your own, and then we'll check it. So go for it. Let's go ahead and check these real quick. Number 29A, 3 consecutive frames without a strike. So a strike is the 0.7, so no strike is your 0.3, 0.3, 0.3, and was that the 0.027? Okay. And now this one, the third frame is the first time she makes a strike. So not a strike, and then a strike. And I don't know what that comes out to be, but you can multiply that. 0.063?
Yeah,
okay. All right, now here, at least 1. So that's 1 minus the probability that none of the 3 are a strike. So that's 1 minus what you got in part A. And so that's your answer. Is it 0.9 something what?
0.09.
Wait,
73.
it's 0.9.
0.973.
Right. Okay, good. And then the part D is just 0.7 to the 12th, whatever that comes out to be. Now let's talk this one here. The train problem. Here we go. So you get stopped. So there's a 15% chance. The probability of getting stopped is 15%. And so you get stopped on Monday and then again on Tuesday. So Monday and Tuesday, but we don't know what happens after that. So those are not included. Don't you put something else on those.
Oh,
That's right. That doesn't mean that the other ones mean you didn't get stopped. No, that's not what it says. You could get stopped or not. We don't know. Okay, now, B, the first time you get stopped is on a Thursday. So you get stopped here, so that one's the 0.15. That's the first time you get stopped. So what happens in front? Not stopped, and Tuesday you get not stopped, and Wednesday you do not get stopped, and Thursday you get stopped. What happens on Friday?
doesn't matter.
We don't know. Okay? All right, you get stopped every day, so all of these are what? Yeah, so you have 0.15 to the 5th power, whatever that is. And then you get stopped at least once during the week. That's 1 minus the probability that none of the 5 get stopped. And 1 minus, if you don't get stopped, what does that mean? They're all good. And so that's whatever that is. Okay, now, we're kind of out of time, but I'll go ahead and I'll give you these ones. This one was 1 minus the probability that none of the 4 tires are defective. So that's 1 minus 0.98 to the 4th power. So you can check yourself on that. And the last one, if you win something, that means at least one of them is a winner. And if at least one is a winner, so if you want at least one winner, then you're going to do 1 minus the probability that none of these 6 are winners.
I made a 79. I could have swore I made like a 90.
Okay? So that's 1 minus
No, I swear.
all. If none of them are winners, then they're all losers, right?
Okay, so
And
it's 0.9.
0.9, all 6 of them are losers. And so that's how you get that.
Okay, thank you.
Okay, and then the homework is page 11.
Okay.
All right.
Well, I can't see how